Hi friends! So we're going to do our third video for our lesson 27 packet. In this third video, I'm going to talk about sort of like a little bonus fun thing we can do with the second derivative. A second derivative can actually give you whether something is a relative min or max. In order to do this, you first need to know a critical value for the first derivative. You have to know somewhere where f prime is equal to 0. If I can find out where f prime equals 0, the next thing I can do then, instead of building the number line for f prime, and you might, in a minute, you'll be like, why would we want to do this? I'll show you. There's a couple times where it's advantageous to do this. Sometimes it's based on the information we're given. If we have a first derivative equal to 0 spot, a critical value, the sign of the second derivative at that location tells me concavity. And if you know the concavity around a critical value, you'll know whether that critical value is a min or a max. If you've got a critical value for first derivative, which means you have a high point or a low point on the graph of f, where f prime equals 0, it's a possible min max or max. If we're sitting at an f prime equal to 0 point, and I know that the curve around that point is concave down, a concave downness around a critical value for f prime equals a max. Because if you're going to be concave down around a point, that point has to be the peak. Vice versa, we have a 0 point. We know the concavity around that 0 point is concave up. Having a 0 point for the first derivative that makes your second derivative positive means I've got a concave up shape around a min or a max. Well, if we're going to have a point and we're going to have concave upness around that point automatically has to be a min. So concave up around a critical value for f prime gives you a min. I don't know that that's intuitive unless you stop and think about the f prime value being a peak or a valley, and then having the curvature around it. So here's a good example. I don't have any information about f, and the only two pieces of information I have about f prime and f double prime are that f prime of 3 is 0 and f double prime of 3 is negative 2. Now that doesn't seem like that should be enough to tell you anything about f, but it does tell you one piece of information about f. If f prime of 3 is 0, then that's possibly a min or a max for f. So x equals 3 is a possible min max of f. This part, the fact that f double prime of 3 is negative 2, that means f has to be concave down around x equals 3. So if you have a point at x equals 3 and you're concave down around it, and that point has the potential to be a min or a max, put all those pieces together, and I know that f has a relative max at x equals 3. This is a little bit like forensics. It's like you're taking little pieces of data, little pieces like one hair here, one fingerprint here, and you're putting it together and saying, I know who the killer is. I have one little piece, two pieces of information about what happens around 3 on the f graph. I have that the first derivative on the f graph at x equals 3 is 0, and that the second derivative on the f graph at x equals 3 is a negative 2. Those two clues together do give me one concrete piece of information about the f graph. I know f is going to have a relative maximum at 3. How do you know when it might be the appropriate time to use this? Well, oftentimes it's in it is a manufactured situation like this, where you're like, how the heck am I supposed to know anything? Just knowing you have a 0 for f prime and a certain type of concavity around it sort of leads you to using this second derivative trick. Okay? You can use the second derivative trick anytime you want. We can use it even back. Oops. Okay. Remember this guy? We had critical values at -2 and 2. My f double prime is 6x. -2 plugged into the second derivative is negative. That's concave down. That made -2 a max. 2 in my second derivative makes positive. There's 2 is a critical value of my first derivative. It makes my second derivative positive. It must be, we must have concave upness around this. And if we have concave upness around this, then that's a min. All right. Let me show you how it can work though kind of nicely sometimes with, I think, trig functions tend to lend themselves well to this. Use the second derivative test to identify relative extrema for g of x. Use the first derivative test for relative extrema to confirm your answer. Okay. So, in both cases, we need to look at that to determine where these minimum and maximums could possibly be. So I need my first derivative. Here's my g function. So it looks like my first derivative is 1/2 minus cosine x. One half minus cosine x equals 0, which means that 1/2 is equal to the cosine of x. I'm looking at the whole unit circle. And so where is my cosine 1/2? Let me stop and think this before I say the wrong thing. Little cosines and big sines are pi over 3 family. Quadrant 1 for positive cosine. Quadrant 4 for positive cosine. So those are my possible locations for mins and maximums. Relative extrema. Ooh, come on, Mr. Mouse. Okay. So, let's do a second derivative test to decide where's the min and where's the max. If g prime is 1/2 minus cosine x, then g double prime, for my little progression here, g double prime would be sine of x. Okay. Sine of pi over 3 is positive. Pi over 3 was a critical value out of g prime, so that means it's a possible min or max for g. We're going to talk about being concave up, g being concave up around pi over 3. So if we're concave up around pi over 3, g has a relative minimum at x equals pi over 3. Boop. Sine at 5 pi over 3, that's quadrant 4, is negative. That means g is concave down around 5 pi over 3. Concave downness looks like this. That 5 pi over 3 is a critical value. It's a place where the derivative equals 0. So g has a relative max at x equals 5 pi over 3. If the first derivative test will work to get mins and maxes, which it is a natural follow through after increasing, decreasing, there's never a situation necessarily where it says you have to use the second derivative. I mean, it could say that, but if the first derivative test will work, the first derivative test is valid. Sometimes the second derivative test might be easier. Sometimes the information you might be given just might lend itself better to the second derivative test. If we wanted to do the first derivative test to verify these, I would have to write this on the next page. I'm not going to do this all the way out. But if I wanted to do this first derivative test wise, I would have to make a number line for g prime. I would put pi over 6 on it. I would put 5 pi over, no, I lied. Those aren't the right ones. Tricked you. I would put pi over 3 on it. I would put 5 pi over 3 on it. I would be looking at 1/2 minus cosine x. And I would be putting numbers in to test that. And what I should be seeing pi over 6. I should see, and this is definitely a little harder because the numbers are a little harder, but this is the behavior you see. To verify that you have the minimum at pi over 3 and a maximum at 5 pi over 3.